Today we're going to do a lab, the purpose of which is to find the index of refraction of a piece of glass. So that means the problem phrased in the form of a question would be, what is the index of refraction of glass? Your materials you're going to see in just a moment when I show you a photograph of the apparatus that we're going to use and explain how we're going to use that. Your variables, I'm not going to go through that with you today either. You're going to see that, if you're paying attention, that is, you're going to see which is your manipulated, which is your responding variable when I show you the data table that you're going to have to record. Of course, you guys know that you have manipulated variable, responding variable in your data table, and your control variables are everything else that you need to keep the same. There's going to be one or two really, really important control variables that you need to list. And there's going to be 1,000 others that you could list. It's the big ones that I'm looking for. Here's what it's going to look like. You're going to each be given a piece of glass and a laser. That's it. Now, underneath that piece of glass, I would like you to place a piece of paper. Okay, I've got some scrap paper up here in the black bin, or you can use lined paper from your notebook. It doesn't really matter. Here's, in essence, how we're going to do this. We're going to turn on this laser. It's going to shine a beam towards the glass. Now, you may see a bit of the beam on the piece of paper. That's why we have that white piece of paper underneath it, so that we can hopefully get a little bit of reflection and see where the beam is going. But even if you don't see it, it's not the end of the world, because you will see the spot at which the laser beam leaves the laser. You'll see the spot at which it enters the glass. And then you're going to see, because it's slowing down when it goes from an index of refraction that's low, which is air, to an index of refraction that's high, which is glass. Because it's slowing down, the angle will decrease. It'll start looking something like this. What you need to do is, for each of these trials, measure the angle of incidence. The angle of incidence is that angle that's measured from that imaginary normal line. You need to measure the angle of refraction, which is that angle that's measured from the refracted ray to that imaginary normal line. Now, how are we going to measure those? As we're looking at the laser? No. What I want you to do on the piece of paper that's underneath it is put some dots to indicate where the lines, where the laser light, laser beams are actually going. And that's going to help you later on to measure the angles. So what I'd like you to do is put a little dot right here where the laser leaves, where the light, the laser beam leaves the laser. Put another dot right here, as close to this block as you can, where you see it entering the block. You will see a clear reflection of a dot where the laser beam enters the block of glass. Put a dot on the paper at that spot. Put a dot on the paper at the spot where the laser beam leaves the glass. Finally, draw a line that's along the boundary there between the air and the glass. The easiest way to do that is to literally put your hand out on the glass and take a pencil and just trace the line along the boundary between the air and the glass. Now, once you remove the block, you can draw with a protractor. You can make sure you have a 90-degree angle between the normal line and the boundary here. Draw the normal line. Okay, draw it at 90 degrees. I mean, not while the block is still there, but once the block has been removed. And then you're going to use a protractor to measure theta 1 and to measure theta 2. You will always find that theta 2 is smaller than theta 1. If you don't, if you find that theta 2 is bigger, you've made a mistake somewhere. Theta 2 has to be smaller because the light's slowing down. Record the value of theta 1, theta 2, and then change the value of theta 1. Increase theta 1, decrease theta 1. I don't care what you do to it. Change the value of theta 1 and see what the value of theta 2 is that responds to the value of theta 1. So get a new set of data there, and then another one, and then another one, and so on and so on and so on. Don't forget to write down that medium 1 is air. Don't forget to write down that medium 2 is glass. And don't forget to write down that the index of refraction of medium 1, which is air, will be 1.00. When you have a table, you know what comes next, right? Whenever you have a data table, you're either going to create an analysis table with it so that you can plot a graph, or you're going to plot a graph right from your data table, one of the two. Well, we're going to plot a graph, but we're going to get the analysis table first. We don't want to plot theta versus theta. We want to plot sine theta versus sine theta. So what I want you to do in this table is to calculate the value of sine theta 1. If you had, say, for theta 1, 30 degrees, then sine theta 1 would be 0.5. If theta 2 is 45 degrees, then sine theta 2 would be 0.707. Right? Literally just sine of whatever the angle is. Then you're going to plot a graph of y-axis versus x-axis. Sine theta 2 versus sine theta 1. And when you do that, it should work out to be a straight line, as they always do for us, work out to be a straight line. You're going to want to display the equation. Y is equal to 0.55x plus 0.003, whatever the case may be. And then you're going to figure out what the slope of the graph represents so that we can ultimately get the index of refraction. So if this is a test question, question might say, here's data. Here's data for sine theta 1 and sine theta 2, or even better, here's a graph for sine theta 1 and sine theta 2. What's the index of refraction? Which is, of course, what we want to get from this. We know how to do this, right? You've done this a number of times now, not for this particular activity in this particular graph, but you've done this for a number of other graphs. You got to get an equation from the graph. If it's a straight line, it's going to be y is equal to mx plus b. And then you got to tailor that equation to this specific graph. So in other words, the y-axis becomes sine theta 2. M becomes the slope. X becomes sine theta 1, because that's what appears on the x-axis. And B, the y-intercept, you're going to find again in this case that the y-intercept is 0 or so close to 0 that it doesn't really matter. The next lab that we're going to do next week, the y-intercept won't be 0. So we're going to have to deal with that. But right now, y-intercept is close enough to 0 that it doesn't really matter. Next step, get an equation from your data sheet, or derive an equation. In this case, it's going to be from your data sheet that has the same variables in there. Can anybody think of an equation from your data sheet that has both sine theta 2 and sine theta 1 in it? Yep. Good. Good. Sine theta 1 over sine theta 2 is v1 over v2 equals lambda 1 over lambda 2 equals n2 over n1, right? We can use any two parts of that equation that we want, probably sine theta 1 over sine theta 2, since those are the variables that appear here, and probably n2 over n1, since we're trying to find the index of refraction of the glass, right? Technically, v1 over v2 works as well, but it's not going to help you get the index of refraction. Let's rearrange this to take the same form as the one from our graph. So our equation from our equation sheet has to take the same form as the equation from the graph itself. So in other words, rearrange this to solve for theta 2. I'm going to cross multiply. I get n1 times sine theta 1. So I'm taking n1 up and multiplying, equals n2 times sine theta 2. Taking sine theta 2 up and multiplying. Then I'm going to divide by n2. So it becomes sine theta 2 equals n1 over n2 times sine theta 1. Now it's in the same form. Sine theta 2 is equal to something times sine theta 1 on both sides. Cross off what appears in both. Sine theta 2, sine theta 1. What are we left with? The slope of the graph is equal to n1 over n2. In n2, that's what we're looking for here. The glass is equal to n1 over the slope. We know the value of n1. Remember, you recorded that in your data table. It's 1.00 because you're going from air to glass. You know what the value of the slope is because Google Sheets spat it out for you when you plotted the graph. 1 divided by whatever the slope is gives you the index of refraction of glass. That's what we're trying to find, right? The index of refraction of glass. Then you got to conclude something. What is the index of refraction of glass? And then how do you know? So you're essentially, for your conclusion, justifying your conclusion by writing in a sentence or two a little summary of what you did right here to get the index of refraction. And then, of course, your sources of error. We want 2 or 3 good sources of error plus your suggestions for improvement. What do you got to hand in for this one? Your problem, which I already gave you. The materials, which is real quick and simple for this, right? There's hardly anything involved in this one. Your variables, manipulated responding, and then a few control variables. Your data, which is the angles. Your analysis, which is the sign of the angles, and your graph. Your conclusion, and your sources of error.